In our last class, we have started the topic processor logic design. We have seen bus organization, scratchpad memory, and two-port memory in our last class. Then we have seen the design of the arithmetic logic unit. Arithmetic logic unit perform arithmetic and logic operation. So if you recall the last class, we have covered this topic in the last class. Finally, we started the design of the arithmetic logic unit. This is the arithmetic logic unit. It can perform arithmetic and logic operation. Our job, we are going to design this ALU. We have seen the design of the arithmetic part of ALU in our last theory class. The basic hardware or basic component that we have used for the ALU design is the parallel adder. This is a 4-bit ALU. Look at what is 4-bit, what is 4-bit. The ALU operation output is 4-bit. S2 is the mode select pin. When the mode select pin is 0, it performs arithmetic operation. When the mode select pin is 1, it performs logic operation. S0, S1, they are the function select. S0, S1, they are the function select. Okay. By these two function select, 4 operations can be performed. Last one is the carry in. If we consider carry in is one of the function select for arithmetic operation, then there will be 3 function select for arithmetic operation: S0, S1, and carry in. So 2, 2, or 3. That means 8 different arithmetic operations can be performed, and we have designed this arithmetic part that can perform these 8 different arithmetic operations in the last 3 class. Look at over here. These are the 8 different arithmetic operations. This is the 8 different arithmetic operation. Okay, and we have designed a circuit for it. What the circuit does? This circuit, there are 2 input A and B, right? So in our design, look at over here. In the arithmetic unit design, the input A, we did not modify the input A. Input A, we did not modify, only we have modified input B. By modifying input B, we have got 8 different arithmetic operations. So this is the modification. This is the modification of input B, and we call this is Y. So our job in our last class was to design a logic circuit that will modify the input B depending on the selection pin. Depending on the selection pin combination, the B is modified. When the selection pin combination is 0, 0, 0 and 0, 0, 1, we modify B to 0. When the selection pin combination was 0, 1, 0 and 0, 1, 1, we did not modify B, kept as it is. When the selection pin combination was 1, 0, 0 and 1, 0, 1, B was modified to B bar. And when the selection pin combination was 1, 1, 0 and 1, 1, then we modified B to all ones. And by this modification, we have got 8 different arithmetic operations. 8 different arithmetic operations. Okay. So we have finally in our last class, we have designed the circuit for this modification. Okay. This is the truth table of this modification. Okay. Look at over here. Since carry in just changed in both cases, so we can neglect the carry in during our circuit design because carry in it came 0 and 1. Okay. So we need to consider mainly S0 and S1 combination. Look at over here. For this S0 and S1 combination, 0, 0, Y equal to 0. When the combination is 0, 1, Y equal to B. When the combination is 1, 0, okay, then Y equal to B bar. When the combination is 1, 1, Okay, combination 1 1, y equal to all 1. So if we summarize this one, this is our truth table. This is the y, this is h0 and so on. Okay, and if we solve it, then we get a equation like this: y equal to b s0 b bar s1. You see, b s0. You see, what's the hyper? b s0 and b bar s1 is the equation of y. Equation of y, and the equation of x, no change in it. X equal to a and y equal to b s0 b bar s1. Okay, so we have found this is the equation of x and y. Y is the modified b and x equal to a unmodified for the arithmetic unit design. So what we do, this is our complete design. This is our x and y is a x equal to modified a, y equal to modified b. There's no modification of a in the arithmetic design, so x1 equal to a1 and y equal to modified b, and the circuit we have designed. Just we will replace the circuit. Okay, just to give the circuit over here for y. Okay, y equal to modified b. This circuit we have designed this circuit. Okay, y equal to modified b. Okay, y equal to modified b. Clear? So these are 4-bit ALU. These are basic hardware full adder. Because our ALU is 4-bit, so 4 1-bit full adder we have cascaded together to get the parallel adder. Okay, 4-bit parallel adder. So this is our hardware for arithmetic operation that will perform these 8 different arithmetic operations. Look at over here. This 8 different arithmetic operations. And we have designed a circuit that will modify b depending on the function select of the hardware. Okay, clear? So we have designed the circuit for y. So this is finally our hardware. Now, then we have seen one example problem. Okay, we have designed another subtractor circuit with one selection variable s and 2 inputs a and b. When s equal to 0, the circuit performs a plus b, and when s equal to 1, the circuit performs a minus b by taking 2's complement of. Okay, so in this region, what we have seen, look at over here. This is our table. Truth table based on the problem setting. When s equal to 0, the circuit will perform a plus b. Okay, the circuit will perform a plus b when s equal to 0, and when s equal to 1, the circuit will perform a minus b by taking 2's complement of b. Okay, so to do that thing, what we need to do, because it is a parallel adder. Okay, our hardware is the this is 1 bit, so 1-bit full adder. 1-bit full adder over here, right? Our hardware is the parallel adder. For 1 bit, just 1-bit full adder we need. So look at over here. Parallel adder, okay? For 4-bit, 4 full adder cascaded together, okay? For 1 bit, 1 full adder. So this is input A and input B. When carry in equal to 0, output is equal to a plus b. Simple addition. And when is carry in equal to 1, and if you do the addition and if we modify b to b bar, instead of giving b, we need to give b bar. If we give b bar instead of b, we get a plus b bar plus 1. A plus b bar plus 1, that is equal to a minus b. So what we are going to do, when s equal to 1, we will modify b to b bar. And when s equal to 0, we will not modify b. Clear? So in that case, we will get addition, and if we modify b to b bar, and when carry in equal to 1, we will get subtraction operation. So this is our truth table. When s equal to 0, this is a and b. Okay, x equal to a. We don't modify a in arithmetic operation. Okay, in this case. So x equal to, look at over here. If I use our pen, this x equal to a, no modification. Okay, no modification. X equal to a, no modification. But we modify b. When s equal to 0, we don't modify b. Keep as it is. Okay, keep as it is, and carry n equal to 0. In that case, we don't modify. Look at over here. When s equal to 0, we don't modify b. B equal to 0, 1, 0, 1. Y equal to 0, 1, 0, 1. No modification. No modification of y when s equal to 0. Okay, when s equal to 0, no modification of y as it is. And when s equal to 1, we modify b to b1. So when s equal to 1, look at what b was 0, now it is 1. B was 1, it is 0. So whatever is b, that get inverted over here. Inverted. Okay. So what is the equation of x and what is the equation of y? Equation of x equal to a, no change. And what is the equation of y? Look at over here. Consider the high one. Okay, consider the high part. This is 1, 1, 1, 1. 0, 1, 0, 1. Okay. So when they are equal, 1, 1. Okay. When they are equal, this is 1, this is 1. 1, 0. Okay, 1, 0 and 1, 1. When they are equal, output is 0. When s and b are equal, look at over here. S equal to 1, b equal to 1, output is 0. S equal to 1, okay, s equal to 1, and s equal to 1 and b equal to 1, output is 0. Okay, look at over here. Consider this one, equation of y. So we will consider the high part, right? 1, 0, output is 1. 1, 1, output is 0. 1, 0, output is 1. 1, 1, output is 0. So what is happening? When b and s are equal, output is 0. When s and b are opposite, 1, 0 or 1, 0, output is 1. Clear? When s and b are equal, output is 1. When they are opposite, when output, okay, look at it again. Look at it. This s equal to 1, b equal to 1, output is 0. When they are equal, output is 0. And when they are opposite, 1, 0, 1, 0, output is 1. This corresponds to logic gate, exclusive OR gate. Exclusive OR gate. So equation of y equal to b exclusive OR x, s, because it is the exclusive OR gate operation. When they are opposite, output is high. When they are equal, output is low. If you consider this s and b, so this is exclusive OR operation. So you can tell that y equal to b exclusive OR s. Clear? Because this is exclusive OR operation. Y equal to b exclusive OR s. Consider this one, b, and consider s and b. These two columns. This is the solution. This is the solution. When, look at over here, s and b, when they are equal, output is 0. When they are opposite, output is 1. So this is exclusive OR operation. So y equal to b exclusive OR s. So this is the equation of x. Okay, equation of y and equation of carry in. Look at over here. When s equal to 0, carry in equal to 0. When s equal to 1, carry in equal to 1. So carry in equal to s. So this is your logic equation of x, y, and carry. Now build a circuit. This is the x equal to a, y equal to s exclusive or b, and carry in equal to s. Okay, so this is a hardware 4-bit ALU that will perform addition operation when s equal to 0, and it will perform subtraction operation when s equal to 1. So this is an example design, short math. Okay, short problem or short design, you can tell. Clear? So this was a topic we have just reviewed that we have done in our last theory class. Now is the time in this class what we are going to do. We are going to do the logic circuit design, the part of the arithmetic logic unit that will perform logic operation. Now we have seen our, look at what here. This is our arithmetic circuit, okay, that we have designed till now. We have completed the design of the arithmetic portion of the ALU, right? When s equal to 0, it will perform arithmetic operation, and when s equal to 1, it is going to perform logic operation. S2, pin number S2 is the mode select pin. Okay, so we have seen the arithmetic design. Now is the time for logic part design. How many logic part design you can do, or how many logic operation you can perform with two selection pin S0 and S1? 4. 4 different logic operation you can perform. And what is the equation of our hardware? Because we are using a single hardware, 4-bit parallel. The equation of 4-bit parallel is the, or equation of parallel is the A exclusive or B exclusive or carry in. Okay, that was the hardware for the arithmetic circuit design. For the logic operation, carry in has no meaning. Okay, for the logic operation, carry in has no meaning. So what is the hardware equation of our logic circuit design? Only A exclusive or B, because carry in has no meaning in logic operation. Clear? So our hardware equation is now A exclusive or B. That's our hardware. Okay, clear? Now, so look at over here. This is our hardware. This is our hardware equation. Okay. Now, for logic operation, the mode select in S2 must be 1. Clear? Mode select in S2 is 1. Now we have two selection pin S0 and S1. When they are 0, 0, if we use the hardware, okay. Now one point over here I need to mention that for the logic circuit design, we are not going to modify B, because we have done it in arithmetic design. We are going to modify A to get different operation, not B. Clear? We are going to modify A, not B, like in arithmetic design. Because this logic design already have modified B, now we will only modify A for logic design. Clear? So look at over here. When the selection pin is S0, they are 0, 0. Already we have done this modification in our arithmetic design. 0, B, B bar 1. That's our design, the arithmetic part. Look at over here. Let me show you. Where is this table? This one. 0, B, B bar 1. That's a modification in arithmetic circuit design. So if I come back over here, zero B, B bar 1. That's the modification already we have done. And A, we do not modify. So this is our design till now. And for logic operation, carry in equal to 0 because carry in has no meaning. Okay, for logic operation, carry in equal to 0. So this is our design till now. Carry in equal to 0, mood select pin is 1, selection pin S0 S1 for logic operation, and this is the modification till now we have done. No modification of A and modification of B, that is in Y equal to modified B, and X equal to unmodified A. So this is our design till now. Okay, with this design, if we use this hardware, same hardware, what things we get now till now? So with this basic design that we have done, with this hardware, what we get? Look at the one again. F equal to X exclusive or Y. So A exclusive or 0, it is equal to A. Okay, so we get transfer operation. But transfer operation is arithmetic operation. We want to perform logic operation. Let's say we want to perform that operation is OR operation. Okay, so what we are going to do? We are going to modify the input A such a way that this hardware, same hardware, will give us the OR operation, not transfer operation. So this item we need to modify. We need to modify A to get OR operation instead of transfer operation, that is arithmetic operation. We want to perform logic operation. Clear? So we'll modify A. That will be X equal to modification of A. Clear? Okay. Analyze the second case till now. In the second case, when selection is 0 is 1, they are 0 1, A was not modified till now, and B is not modified. B is as it is B. In that case, what we get? Carry equal to 0 for logic operation. In that case, with the same hardware, we get A exclusive or B. Fine. So no change we need to make for this OR operation. So no change we need to make. Fine, perfect. We don't need to make any change on the second case. Okay. Third case. Third case was when the selection is 0 S1, they are 0 1, and A equal to unmodified A, that is X equal to unmodified A, and Y equal to B bar, and carry in equal to 0. So in that case, what you do? With the same hardware, it is X exclusive or B bar. X exclusive or A exclusive or B bar. Look at it for it. A exclusive or B bar. If you simplify it, we get NOR operation, exclusive NOR operation. A B or A bar B bar. This is exclusive NOR gate. This is exclusive NOR gate. So we get NOR operation, or sometimes it's called equivalence operation. In this case, when both A and B are equal, output is high, right? Output is high when they are both are equal. Opposite of exclusive OR operation. This time we call equivalence operation. When inputs are same, output is high. Okay, inputs are same, output is high. So we get exclusive NOR or equivalence operation. But we don't want that equivalence operation. What we need? We need AND operation, for example. We need AND operation. So this third option we need to modify. We need to modify A to get the AND operation, not the equivalence operation. Because we want to get AND operation on the third case. That's our requirement, for example. Look at that. When this is a hardware, X exclusive or Y. So when X equal to A and Y equal to B bar, A exclusive or B bar, if you expand it, it becomes exclusive NOR gate. In the exclusive NOR gate, when inputs are equal, output is high. When inputs are same, look at over here. When inputs are 1 1, output is high. When inputs are 0 0, output is high. This is equivalence operation, exclusive NOR operation. But we don't want it. Our design required that. Okay. On the third case, we want to get AND operation. Okay. So what we need to do? We need to modify input A. Okay. To get the AND operation. So on the first case and third case, we need to modify our input A. Fourth case, when selection B is 0, S1, they are 1, 1, and till now we have the design X equal to A and Y equal to 1. This is our design till now. So if we do A exclusive or 1, we get, let's look at it, A exclusive or 1. If we do like that, we get invert operation, not operation. We get not operation. Fine. Not operation is fine with us, that we need. So second case and fourth case, these two cases, we don't need to make any change. Only first case and third case, tick mark. First case and third case, we need to modify input A to get OR operation and AND operation. Clear? So how we can get OR operation in the first case? Let's play a trick. What is the trick? Very simple trick. Look at over here. We will modify A. So instead of A, if we give, when the selection pin is 1, 0, 0, A or B. Instead of A, when the selection pin is 1, 0, 0, we give A or B, that is X equal to A or B. If you do like that, we get OR operation. Very simple trick. Okay. So when the selection pin is 1, 0, 0, our hardware will supply instead of A or B. So X equal to modification of A. It will be A or B. Then we will get OR operation. Okay, clear? Look at value. And how we can get the AND operation? How we get the AND operation? Modify A such way, get the AND operation. Let me show you how we can gain AND operation by modifying A. So look at over here. This was our logic question for the parallel ladder for arithmetic unit design. Okay, and this is our equation for the logic unit design, basic hardware. So look at over here, how we can get an operation instead of equivalence operation. Okay, let us check the possibility of ORing each input A with some Boolean function k and taken as k equal to b bar. Then we get with the hardware A is or B. What things we get? Look at over here. We have modified A. We have replaced A with A or B bar. Okay, we have replaced A with A or B bar. Then we are using our same hardware. At that time, you see, it was B bar, Y equal to B bar. So if we do this exclusive OR operation, what we get? If we expand it, we get AND operation. Have you found the trick? So what trick over here? X equal to what A modified A. What modification of A we have done? A equal to A or B bar. If you do like that, if you use as a basic hardware, parallel hardware for logic unit design, if you expand it, look at over here. If you expand it, it becomes AND operation. You see, just expand it. Expand it. This it becomes a AND operation. Okay. So what we see? To get the OR operation, we replace A with A or B. when the selection pin is 100. When the selection pin is 101, no modification we need to make. Already explained our operation. When the selection pin is 110, we need to modify A with A or B bar to get the no. Yes, we need to modify A with A or B bar to get the AND operation, like we have seen. Okay, clear? On the selection pin is in 110, we need to modify A. Instead of A, we need to supply A or B bar. Then if we perform express operation with the hardware, we get AND operation. Okay. On the fourth case, no need to change anything. So we need to modify case 1 and case 3. Okay, case 1 and case 3. In case 1, we have modified A with A or B, and in case 3, we have modified A with A or B bar to get the AND operation. Now with the hardware design part. So this is the summary. This is the summary of all the function. Look at over here. It is the complete design a 2-bit ALU for the operation listed below in the table. Okay. Now let's summarize all the concept in a complete problem form. What is the problem? Design a 2-bit ALU for the operation listed below in the table. Look at over here. Register R1 holds the variable B. Register, okay. This is word A, word B, and this is the 7 register that can have the A and B. Okay. Register 1 to register R1 to R7. There are 7 register. This register will hold the value of variable A or B, right? Or the result, whatever it is. Input, output. These are temporary registers, the registers. Okay. Now, when function with carry equal to 0 and function when carry equal to 1. So we have summarized. Look at over here. Depending on the selection pin, S0, S1, and S2. Okay. When okay, we need to get this up. This is a transfer operation we are getting. This is the increment operation we are getting when carry equal to 1. This is the addition operation. The addition with the carry A plus B bar. And this is the subtraction operation. Okay, A minus B. This is the decrement operation for the selection pin. This is the transfer operation. This is the logic operation. 4 logic operations. So 8 arithmetic operation and 4 logic operation. A or B, A exclusive or B, A and B, and NOT operation. Yes? Again, let me explain. When carry equal to 0, we have got this operation for this selection pin. Okay? Transfer operation. When carry equal to 1 for this selection pin, we will get increment operation. Okay? This arithmetic operation, 8 arithmetic operation in this case. For this selection pin 001, when carry equal to 0, we want addition operation. When carry equal to 1, we want to get add with carry. Okay? 8 operations. Look at over here. 4 operations. Then 5th operation. When depending on the selection pin 010, A or B bar. This is subtraction operation, A minus B. B bar plus 1 is minus B, right? So this is subtraction operation. 6th operation. When the selection pin is 110, decrement operation. Transfer operation. So what we have got? We have got, in this case, 8 different operations. 8 different operations. Arithmetic operation. Okay? We need 8 different arithmetic operations depending on the selection pin. Clear? When carry n equal to 0, these 4 are arithmetic operation. When carry n equal to 1, these 4 are arithmetic operation. In total, 8 arithmetic operation. When carry n equal to 0, okay, when carry n equal to 0, that means carry n has no meaning. It can be 0 or 1, it does not matter. Carry n can be 0 or carry n can be 1. It does not matter for logic operation. We need 4 different logic operations, A or B, A exclusive of B, A and B, and invert operation, not operation. Okay, and in arithmetic operation, we have seen we modify B. What modification of B we have done? We have seen, right? This is the modification of B we have done for arithmetic operation. This is the modification of B in terms. This is Y modified B. Y equal to modified B. And for the logic operation, what we have done? We have modified A. X equal to modified A. Okay, X equal to modified A. The first case, we have modified X equal to with A or B. In the second case, we did not modify X equal to A. In the third case, X equal to A or B bar. In the fourth case, no modification. Okay. So that's our modification for logic operation. So with that modification, we will get this 4 different operations. Clear? And when carry n equal to 1, also same thing you can get, because carry n has no meaning. It can be 0 or 1, does not matter. Okay, for logic operation, we get 4 different logic operations and 8 different arithmetic operations. Okay, and how we can get? By modifying B in arithmetic operation, by modifying A in logic operation. So let's summarize the entire fact in another table. Look at over here. This is the output we need. Let's summarize from the previous table. This is your selection mode select pin, selection pin S0, S1, and carry in. Okay, and this is the operation we need. Just summarize. Okay, from the previous table. This thing we need. This operation we need. And how we get this operation? For the arithmetic part, what we have done? We have modified Y. Y equal to modification of B. So for the first case, no modification of Y equal to 0. For the first case, two case. Okay, Y equal to 0. We have modified B to 0. Just previous design. Okay, same thing. For the second two case, B bar plus 1. This is B bar plus 1. This is B plus 1. It's A plus B plus 1, not B bar. A plus B plus 1. Okay, we have modified B. No modification of B. Look at over here. Zero. First case it is 0. B was 0. Second case, no modification of B. Third case, B was modified to B bar. Fourth case, B equal to 1. So first case it is 0. Second case B equal to B, no modification. Third case B equal to B bar. Fourth case B equal to 1. To get this 8 different arithmetic operation. Clear? So this is wrong. Okay, this is clear. Now for the logic operation, we got over here. In the first case, for to get the operation, we have modified A to A or B. Second case, no modification. Third case, A was modified to A or B bar to get the OR operation. Fourth case, no modification of A. So this is X equal to, for the arithmetic operation, no modification of A. For the logic operation, we modify A. So this is X is equal to modified A, right? And what is the Y? We can modify B. For the logic operation, we don't modify B. kept as it is, 0, B, B bar 1. Clear? So X equal to modified A, Y equal to modified B. Entire design. Now we are going to do entire design. Complete combined circuit. So if we can find the logic equation of X and logic equation of Y, then our design is complete. Entire ALU design, combined design. Clear? So let's find the logic equation of X. How to find the logic equation of X? Look at over here. We need to do the K-map. Okay. In the K-map there are three variables. Look at over here. S0, S1 and S2. Depending on the arithmetic logic circuit design, okay, depending on the S0, S1 and S2. Okay. S0, S1 and S2. So if we solve for X, okay, look at over here, S0, S1 and S2. S0, S1 and S2. If you solve for X, okay, look at over here, S0 can be 0 or 1, then S1, S2, okay. So S0 can be 0, 1, S1, S2. So when they are triple 0, S0 is 0, S1 and S2 are 0, 0. Okay, triple 0. What is the value of X? Look at over here. When they are triple 0, value of X equal to A. Clear? When they are 0, 0, 1, value of X equal to A. Just fill up the K-map. 0, 0, 1, value of X equal to A. When they are 0, 1, 0, 0, 1, 0, 0, 1, 0. What is the value of X equal to A again? Similarly, fill up the table. When there are triple 1, X equal to A or B bar, X equal to A. When they are triple 1, and when they are 1, 1, 0, X equal to A or B bar. When they are let's say 0, 0, 1, X equal to A or B. And they are 1, 0, 1, X equal to A. From the previous table, just fill up the K-map. Clear? When you fill up the K-map and solve for this X, because this is the equation of K-map for X. Okay, when you solve it, look at upon here. One is the outer part, outer inter I think block. All A. This one block. Another block A or B bar. Look at over here. So X equal to, for the bigger block, A, right? Common A. Second block, A or B bar. So S2, look at over here. This is S2, S1. They are both 1, 1. And S0 bar. In this case, for this green color, S1, S2, they are 1, 1. And this is S0 bar. So S0 bar, S1, S2. B bar. For the green color block. For the blue color block, look at over here. For the blue color block, this is S1 bar, S2, S0. Look at over here, S0 bar. So S0 bar, S1 bar, S2. S0 bar, this is S0 bar. Okay. S1 bar, S2. D. Okay. So this is the equation of X. Similarly, this is the equation of Y. Okay. For the Y, again, you do the K-map and you take one block, red color block, green color block, and what happens? The equation of y. Already we have done it. Another way, we have seen it for a combined form. Okay, so equation of y equal h0b s1 b1. We have seen this equation before. The new thing is the equation of x. Okay, from the schema. This one already we have done in combined form. Again, it is very simple. Okay, from the previous table, this came up for x. This is the came up for y. Okay, so we have got the logic equation of x and y. What is the logic equation of carrying? Again, came up. This is 4 variable. For 4 variable, we need 16 location in the cell in the came up, right? Carry in S0, S1, S2. Depending on the value, if you plot, if you place the value in the came up, it becomes like this. And if you solve for it, look at over here. Red color block. Okay. This S1 get changed, S0 remain fixed. So S2 bar, S2 remain fixed. So S2 bar. And this 0, 1, 1, 1, 1. Okay. So carry in remain fixed in this case. Okay. 1, 1. So carry in fixed. S0 get changed. So we'll neglect discard S0 on the vertical line. S1 varies, will discard S1. We keep S2 bar. So S2 bar carry in. S2 bar carry in. Is the logic equation of Z, that is modified carry. So this is our logic equation of X, Y, and Z for a combined design of this one. Clear? So once you have the logic equation, just to go for the circuit logic circuit design. And this is what looks like complex. It's not a complex like this. Just follow the equation. Just follow this equation. Okay. What I suggest in your exam hall, draw logic circuit for these 3 equations, X, Y, and Z. And in the complete design, let's say this 2-bit ALU, first bit and second bit. Okay, first bit and second bit, just X equal to, already you know the circuit, just give me X1, X2. You don't need to draw the circuit again in your exam hall. Okay, it will waste time. Just give X1 and Y1. No need to draw the circuit because we have drawn the circuit over here from this equation already, separate circuit. So in the combined circuit design, okay, just give X1, Y1, X2, Y2. Already you know what is the circuit for X and circuit for Y. And this is the Z, Z1, Z2. Okay. So 2-bit, you'll draw 2 blocks. For 3-bit, you'll draw 3 blocks. For 4-bit, you'll draw 4 blocks. For 8-bit, you'll draw 8 blocks. But you don't need to repeat the complex design again in your exam hall. It will only waste the time. Just draw one time from this equation and give XY. In terms of XY, simple circuit you draw. Okay. So this part, this portion, you don't need to draw on the exam hall. Okay. Just draw this simple part. Draw XY separately and draw this simple part. For 2-bit ALU, 2 blocks. For the 4-bit ALU, 4 blocks. So that's the design, complete design of the arithmetic and logic unit. Any question? If you draw the circuit separately for X, like for X and Y and Z, then in the final design, you don't need to draw the circuit again and again. Just give only X and Y. Just draw your circuit in terms of X, Y, and Z only. Okay? You don't need to repeat the entire drawing on the left side of red color again and again. It will only consume extra time in your exam hall. Just draw your circuit, simple drawing you do. Right side part only. In terms of X, Y, and Z. That's all. Clear? Another question,